Welcome back to this series of lessons in which I explain Tomasulo's algorithm. The purpose of this lesson is to give an example that shows how a sequence of instructions is scheduled dynamically using Tomasulo's algorithm. Here's the example that I will use. A multiply double instruction, an add double that is data dependent on the previous multiply, and finally a subtract that is not data dependent on the previous two instructions but is output dependent on the multiply, since both the multiply and the subtract write register F0. I also assume that the instructions have already been fetched into the instruction queue as shown here. Notice that for ease of association I use a red color for the multiply, a blue color for the add instruction and a green color for the subtract. Notice also that to make things easy, floating point register file floating point register Fi is initialized with I.0. First, the multiply instruction is retrieved from the head of the instruction queue and issued to reservation station mul1. Both its operands are available in registers, so it is issued together with its operands value 1.0 and 2.0. Furthermore, the RS field of register F0 is set to mul1, indicating that this reservation station will produce a result for register F0. Next, the blue add double instruction is issued. It is issued to reservation station add1. Its first operand, F0, is not available, so it is issued together with the identifier of the reservation that will produce this value, mul1, as found in the register file. The second operand, F2, is available, so the instruction is issued together with its value 2.0. Furthermore, the RS field of register F3 is set to add1. Notice that implicitly we have performed register renaming in hardware. After the add double has been issued, it no longer waits for register F0 to become available. Instead, reservation station add1 waits for the result of mul1 to become available. This way, Tomasulo's algorithm eliminates name dependencies. In the next cycle, the subtract double is issued. It is issued to reservation station add2. Since it is not data dependent on the previous instructions, it issues together with its operand values 1.0 and 2.0. Furthermore, the RS field of register F0 is set to add2, replacing the mul1 identifier that was there before. So the result of the multiply is never actually written to the register file. Now the multiply and the subtract can both be executed. In fact, the execution of the multiply has already begun. So we have to choose which instruction finishes first. I will assume that the multiply finishes first. The instruction in reservation station add1 is waiting for the result of the multiply instruction. So, when the multiply instruction has written its result onto the common data bus, the first operand of the add instruction in reservation station add1 has become available, and this instruction is now ready to execute. Now both the add and the subtract instruction are ready to execute. But since the subtract was ready already in the previous cycle, it is reasonable to assume, and I will assume, that it will finish its execution first. So next, the subtract instruction will write its result -1.0 to the register file as highlighted here in green. The reservation station add2 is freed so that it can be reused for another instruction, and finally only one instruction remains, the add double in reservation station add1. Finally, the add double will write its result 4.0 to register F3, completing the execution of this sequence of instructions. I end this lesson with a list of features of Tomasulo's algorithm. First, as shown, Tomasulo algorithm implements register renaming through the reservation stations, thereby eliminating name dependencies. That is, write after read and write after write hazards. In fact, the reservation stations and the normal register file can be viewed as a virtual register set, providing more effective register. Notice also that the reservation stations have a distributed structure, allowing an operand to be sent to multiple reservation stations in a single cycle. This would be very difficult to achieve with a centralized register file, since accesses to a centralized register file need to be serialized if the number of accesses exceeds the number of read ports. A second feature of Tomasulo is that it implements bypassing or forwarding via the common data bus. A result is forwarded directly from an execution unit to potentially multiple reservation stations waiting for it. Third, Tomasulo implements in-order issue or dispatch. Dispatch is just another word for issue. Instructions are issued from the instruction queue in FIFO order, which corresponds to program order. Instructions are executed out of order, however, depending on the availability of their operands. Finally, instruction retiring or completion, which occurs when the result of the instruction is written to the register file, is also out of order. This implies that Tomasulo does not support precise exceptions. An architecture is said to support precise exceptions when all exceptions are raised in program order. Imprecise exceptions cause a problem when we need to restart the program after the exception, because some later instructions have completed while some earlier instructions have not. This completes this lesson. Thanks for watching. In the next lesson I will extend Tomasulo's algorithm with memory access instructions, loads and stores, since they require special attention. Hope to see you back.